Go!
Good morning, ladies and gentlemen. Let's do this now. How much momentum does a 1,500 kilogram car going 20 meters per second have?
What is that equation for momentum? Let's see. It's P is momentum. P is equal to...
Mass times velocity. Okay, what do I do with that calculator? Hey, calculator. Oh, I think it's under here. There it is. Okay. All right, so we just do our mass times our velocity. Easy does it. 1,500 times 20, and I get 30,000. I could have done that one in my head.
Kilograms, meters per second.
Okay, number 2. If a 750 kilogram car has the same momentum, what is its velocity? So, cancel. Velocity is going to be the momentum, which is that. Now see if you can make a prediction here. How do you think it'll be going faster or slower? What was the mass? 750?
750, it's a lighter car.
Meters per second.
So if it's less mass, it's going to be a bigger V.
Divided by 750. There it is. 40, just 40 meters per second. Bada boom.
Oh, you know what? 750 is half as much as 1,500.
Yeah.
So that means it's got to be going twice as fast.
So what we have here, yeah, that's perfect. So we have we have big M, little v, little m, big V.
That's right.
E. Okay. All right. Why is the impulse momentum theorem important to your survival?
We're going to ask you to get up out of your chair wherever you are. If you're laying on a bed or if you're driving in a car, it's going to be hard.
Come on, get up. Yeah, I'm talking to you. Okay, this couch is so comfortable. I know. Okay, so I'm going to ask you to jump up in the air.
Okay, but this time, look at your knees when you jump up. Let's do that again. And jump.
Let me get over here too. And I want you to pay attention to what your knees do.
Side.
Good?
Okay, yeah.
Good, get right here?
Now
Okay.
stay where you are. I want to
Okay.
watch what your knees do. Okay, do it again. Oh, okay. Everybody do that? Everybody feel that?
Have you done it? Do it now. I can tell. No, I'm just kidding. I can't tell. It's done.
If you jump up in the air again to exactly the same height, you'll have exactly the same momentum when you come down, right? Mm-hmm. What are we going to do this time?
And my mass is the same, but this time my legs, I'm going to keep my knees straight.
You're going to keep your knees locked as well. Lock them, okay?
There we go. Locked. Okay, I'm going to jump up and then...
How did that feel, boys and girls?
Uncomfortable. I'm like tensing, clenching so I don't hurt myself here. And so it doesn't feel good, does it?
Nope.
And why is that? Should I go to the next slide here? Or
Sure.
Should I? So we know that impulse changes momentum.
So you had some momentum just before you hit the ground, and then that went to 0. So your momentum changed. And if you jump the same height both times, the change in momentum was the same. That means you required the same impulse to change your momentum. What's the next slide?
This guy right here.
Ah,
Bada boom.
so the impulse is the same.
Okay, so the impulse changes momentum like we just talked about.
Yeah.
The mass and the velocity were the same like we just said.
Yeah.
But we experienced some different feelings, right? When we landed with our knees bent, it didn't hurt as much. There was not as much force. But when we had our straight legs, it hurt more. And why is that? Because we're changing the time interval, right?
When you bent your knees, you increased the amount of time it took to come to a stop.
Yeah. You have more koosh.
That's right.
Okay, more koosh. More koosh, less force to make this stay the same.
When you land with your knees locked, you come to a stop right now.
Less time, more force, ouch.
That's right.
Okay. Momentum and impulse are both vector quantities. What does this mean?
Magnitude and direction.
Magnitude and direction. If impulse and momentum are in the same direction, momentum increases. If they're in opposite directions, momentum decreases.
You guys are putting this stuff in your notes, right?
You guys are writing this down, right?
Of course they are.
Yes, what's more? Anything for you? Okay. All right, so what does this mean? Okay, this means that, so it says if impulse and momentum are in the same direction, momentum increase. I need more space. Okay, so this ball is moving, it has momentum.
Yes.
I'm gonna add an impulse in the same direction,
Oh, it went faster.
and it went faster. Okay, now pause. Okay, now, oh, actually, let me go back over here. So they can get the same direction here. So we're gonna do the same thing over again. Okay, I have this momentum doing its thing. Okay, but now I'm gonna apply my impulse in the opposite direction, and it slows down. Oh, actually, I went too hard for that, huh?
Don't know your own strength.
Let me do it again, okay?
Plan.
Momentum. Oh, it's harder to do than it looks.
Well, the momentum decreased.
The momentum
Here,
decreases.
just push it over to me.
Watch
Here
the
it
pressure.
comes and boom. I applied a force in that direction. It decreased the momentum.
Exactly.
Let's play soccer.
Maybe. Oh,
With volleyball.
Miss Warner around the world.
Don't expect a header with this thing.
Yeah. Okay, we're gonna put that right. You guys notice that our room has so much space right now? It's because they're cleaning the floors. Okay. So you guys saw that we were able to make the momentum increase when we added that impulse to the momentum, and we made it decrease when we kicked it the other direction or just stopped it.
That's right.
Okay. On a force versus time graph, the area between the line and the x-axis is the impulse. Oh, didn't follow through.
Okay, page 201. I'm going to come around on this side.
Okay. So what does that mean? That means that this purple part right here,
What kind of a graph do we have here?
well, we've got time in milliseconds, and we've got force. So force time graph, which means that the area between the line, this is my line,
Yeah.
and the x-axis is the impulse. So if I was to calculate what all that purple part would be, that would be the impulse.
So that's if you hit something with a tennis racket, it comes in and it first starts to touch. It's kind of like the football. It's kind of like the koosh ball. And so the force isn't all at once. It creeps up on you.
Yeah. So this is right in the very beginning when the tennis racket and the ball first make contact, right?
Yep.
And they always tell you in tennis, if you didn't know this, to follow through. Oh. And why is that? Well, the more contact we make, the more force we apply over that time that the ball and the racket are making contact,
The
right?
greater the time, the greater the impulse.
And this is exactly the same. So I am a basketball player, and whenever your like 3-point shot or your free throw isn't going in, one of the things that they will tell you is to follow through.
Yeah.
And why is that? Well, the longer that your hand stays on the ball, the more force and control you have over the ball. So if I, go like this, okay, I'm not in as contact with the ball.
You
as
came off with the palm of your hand.
Yeah, like wasn't, but a follow through means we're gonna have as much contact in the ball throughout the entire thing. Okay, much more.
Rolls off your fingers.
Yeah, and-
Longer time.
And same with soccer, right? They tell you to follow through when you're playing soccer. I'm not gonna kick at you, but
Go ahead,
okay.
kick it.
I'll kick at the door there. Okay, right?
Sweet.
Okay. So I almost hit the fire.
And in baseball, when you're swinging through,
Yeah.
boom.
I don't even know baseball, but it's the same exact principles, right? And so, especially with baseball, the longer you are in contact with the ball and the bat, the more force you're going to be able to exert on that ball.
The more impulse, the more the change of momentum, the
Yes.
faster it's going to go.
Yeah, don't forget, the impulse is the area underneath that curve. The more the force over time, the more the area into that curve.
That's right.
Okay. Can you solve this for each variable?
How would you solve for force, Ms. Mo?
We just divide by delta T over there.
How would you solve for mass?
Divide by mass, put it over here.
So whatever you want to find, divide by the other thing on the other side.
And get the answer. Okay.
Uh-oh.
Whoa. Do not let this intimidate you. It's really not very scary because, in fact, the trick to this is just to look at two things and ignore everything else.
We got a bunch of stuff that's all equal to each other.
It's all equal to each other. And so I could look at these two, this equal to this. I could look at this and say, hey, that's equal to this. I don't have enough hands to cover everything. I could say that this is equal to this. right here.
Yeah.
Right there. So all that you have to do is pick the two equations, this and this, this and this, that and that, whatever.
Because the impulse momentum theorem, impulse changes momentum. What's impulse? Force times time. When momentum changes, that's the final minus the original. And when the momentum changes, it's the velocity that changes. And when the velocity is changed, it's the final minus the original.
It's all the same.
They're all the same.
Okay, and you guys just showed me that you guys could divide by anything and get what you need to solve for. It says probs at the bottom.
Yeah, it's the next one.
Okay. What is the momentum of a 220 kilogram SUV going 26 meters per second? So first we want to figure out what
We
the
could find
momentum
that
is.
out, couldn't we? I don't think we have to. We could find it out.
We could.
Okay.
How would we do that? Should we look at our uh-ohs?
Yeah.
Okay, so we've got the mass and we've got the velocity.
It's mass times velocity over here, but it's a changeable. Oh, let's go back to the problem. I stopped you too soon.
So we've got the mass. Let me write these up here.
All right.
So we've got the mass.
2,200 kilograms. The velocity is 26 meters per second.
Okay, that probably means that it was starting at 0 at one point, right?
Well, no, it's just going along. It's got that velocity. The question is, what force is required to stop it?
This is why you should always read the question, ladies and gentlemen. What force is required to stop it? And then it gives you time. So in this case, we have, what, 21 seconds for letter A? We'll start with that one.
So now let's go back to the uh-oh.
The uh-oh is everything.
So when it stopped, what's its final velocity when it stopped?
Well, when it stops, it's eventually going to be 0.
So where would that be
So-
on here?
That means that the final velocity would be 0. We have our initial velocity,
Okay,
right?
so we could use that last term. M equals
Okay.
that one, yeah?
I'm gonna write down. We said our. Oops. This would be our initial. This would be our final.
Yeah.
Okay, so I'm gonna say M V final minus V initial. Okay.
Yeah.
Now, what else do we have? We're trying to
Well,
figure out force.
Force, and then we got time.
Okay, well, this is the only one with force right here.
Yeah. So check it out. We can ignore everything except force times time in that last one.
Okay, and I can set them equal to each other. Okay, and I can just divide by my delta T.
And it's always better to solve with the variables instead of plugging the numbers in. So now you can plug the numbers in.
Second, all divided by, it's just
21 seconds.
21 seconds. Okay, so I'm just gonna do 2200 times a negative 26, and I'm gonna divide that by 21, and I'm gonna get negative 2,724. Okay, negative
724 newtons.
2,004 newtons.
What does the negative mean?
It's just the direction of the force.
Yep, so the force has to be in the opposite direction of the motion in order to stop it.
Oh, right there. Okay.
What would be different for letter B?
Okay, so what force is required to stop it in 5.5 seconds? Well, the only thing that we change is this bottom part, right?
Yeah, just do it in your calculator. We don't need to write it down because you got it in.
Okay.
You know how to use the cheat button in a calculator?
How do I get that guy back up there?
Hit Shift
Shift,
and then Enter.
enter.
And there it is again. You should be able to just toggle over and change the number on the bottom.
Oh, you're right. Oh, good. I like it.
I call it the
Smart
cheat button.
Mr. Boy Guy.
Yeah, it's a cheat button.
Okay, so negative 495. 400. That's working right.
Okay, no, that can't be right.
Oh, did I mess up the top part? I know. I'm like, it's so much less.
Yeah, so what you've got then is you're going to have the.
Let me check this out. 57200 divided by 5.5. Oh, there we go. I don't know why. I don't know why it didn't have me do that. Okay, so we actually have negative 10,400.
That's a lot more.
No, that's more like it.
So you got to put the brakes on a lot harder to stop it. I mean, if you're stopping at 21 seconds, you're barely touching the brakes. 5.5 seconds, that's a little bit harder. Now, I noticed it's 0.22 seconds. What would be required to stop something in 0.2? That's
Um,
less than a second.
A lot of force.
That's
for
like
sure.
hitting a bridge on the highway.
Should I do it in there?
Yeah, just
Okay, so here we go. Now I got this going there. 0.22, and I get negative 260,000.
260,000 newtons. That's where people get killed.
It's no good.
No, that's not enough koosh.
Not enough koosh, for sure. Sweet. Okay, so you guys see how we did this? We wrote down what we had here, and we knew we were going initially 26 meters per second, and it says what force is required to stop it. And notice how I didn't tell you that the final velocity is 0 meters per second, but we know we're stopping.
It's
So we know it's gonna be.
inferred. It's inferred.
And so then we use our equation, and we say, okay, I've got mass, my two final velocities, write that one down. What am I trying to find? Force, get rid of the
So
rest.
ignore everything but what you need.
Mm-hmm.
All right, there's some homework here.
Homework, page 205, number 4 and 5.
You can do this. You can do this.
That's right here, number 4. Now you guys ready for this one? And number 5. Good luck.
Page 205. Boom.